Hey, Vera. You're muted. We can't hear you.
Hello, hello.
Okay, Joyo, I hear you. How about you, Vera?
Nice.
Hey.
There you are. Okay, great.
I'm great. Yeah, I'm
Perfect.
here. Can I share my screen?
Sure.
So I will be ready. Should you give me? Yeah, great.
Yeah, I'm trying here. Hang on.
Yep.
There you go.
So I will do. You can see, right?
Yep.
I will do it like this. Okay, that's not it. Okay.
There you go.
No, that's not it. I will put it here. Just a second. Okay. That's what we need. You. Okay, that's better.
Looks good.
Yay. So I am ready.
Cool. We'll give a couple more minutes, and then Joyo is going to mention a workshop. We'll introduce each other and then introduce you, and off you go.
Great. I will mute myself in the meanwhile.
Okay, thank you. Good morning, folks, and good afternoon to those of you in different time zones. We're going to give one more minute here, let people continue to filter in, and then we'll get started. All right, good morning or afternoon. Welcome to track 2 for GRIMMCon. My name is Jeff Jones. I am the Director of Sci-Fi Engineering and ICS here at GRIMM, and I'm joined here by my colleague Joyo. Go ahead and introduce yourself, Joyo.
Hi, everyone. I'm Joyo. I'm a Senior Software Engineer at GRIMM. And just to give everyone a fair warning, videos throughout this talk may have different volumes, so we'll just do a volume check before and after. just to make sure nobody gets their ears exploded. But I think Vera's good to go. But before that, I wanted to mention that at 12 o'clock, Ian Garrett is hosting a workshop on our Discord, which I'll put that QR code back up, but that was what was up earlier. You can also visit the GRIMMCon website to find the Discord link if you don't want to trust a QR code. I don't blame you. Anyways, that begins at 12 o'clock Eastern Daylight Time, and that's all.
Awesome, thank you. It's my pleasure to introduce to you today Vera Menz. Vera is a vulnerability researcher at Claroty. She's passionate about low-level security and electronics. Vera began her career as a low-level software engineer, but later transferred to security research and then vulnerability research. Today, Vera uses the same mistakes she made as a developer to find bugs. Vera, we're honored to have you with us, so take it away.
Hey guys. So can we start, right? Can you hear me?
Yep, all good.
Great. So hello everyone, and thank you for joining. Today I'm going to talk to you about a research project that we conducted at my team at Claroty, especially Rick Katz, Sharon Brazinov, Tal Karen, and myself, along with Shahar Menashe from GFOG. And the name of my talk is Unboxing Busybox, and soon you will understand why I called it that. So a little bit about myself. I'm a vulnerability researcher at Team 82. Team 82 is a vulnerability research team at Claroty. So what we mainly do, we focus on SCADA, OT, IoT, and mobile projects. We pick a target and we research it for vulnerabilities. Then we disclose them to the vendor. And when vendor patches those vulnerabilities, we are free to talk about them. And that's what's happening right now. So let's go into the interesting stuff. So what is Busybox? Let's talk about it in the first place. And if you are not familiar with it, you can think about any Linux distribution that you have saw. In every distribution, we see LN, LS, MQTIR, chmod binaries. We are all familiar with those. They are all compiled differently and separately, and they take space. There is a lot of them, and it seems that in embedded devices, the space is very limited, and the use of those executables are not that extended as in general computers. So the idea of Busybox is simply to take all of those executables and put it in one single executable. So instead of managing multiple executables, we can now manage only one, which will trigger the functionality of all the others. It will make the space much more efficient because it takes much less space, and it will be much easier to manage, and we will see why. But first, let's see how it's used in practice. So here we can see the bin-ls program that we are all familiar with. And on the left, we see the ls program being executed on a general computer as we are used to. And on the right, we see the ls with the same input is executed from the Busybox binary. So the main difference here is that ls is right now is an argument to Busybox executable, in contrast to the left picture in which the ls is executable by itself. So that's a bit for the usage. And this is how it looks like. I did a listing of bin directory in some embedded device, and we can see that all the executables that we are familiar with are, right now are just soft links to one really much smaller than all of being combined together executable, which is Busybox. And on the right side, we can see the Busybox main page, which is just a version and all executables that contained within Busybox binary. And it is important to note that a vendor that compiles the Busybox executable, he can choose what applets will be included and what applets will be excluded, and thus limiting the attack vector for its device, and potentially and also suppressing the space on the disk. So that's great. Is very convenient for the vendor, and he should use it. And as we see in this Wikipedia page about Busybox, it is de facto suit for use in embedded devices. We can see it in our routers, in our IP cameras, and all IoT devices that you can think of. And this should tell us that a research on such a binary, such executable, can be valuable for the community, because finding vulnerabilities in this program can do an impact on multiple devices, and some of them are critical. So let's go again about advantages of Busybox. It's small in size, only a couple of megabytes within a tar file, and it's have centralized management. It means that only one compilation is taking place. We compile only the Busybox executable, and all the applets are going to be compiled within it. And a special one is that the vendor can exclude some applets from the Busybox utility, and thus limit the space that it takes, along with limiting the attack vector on the device, as I said before. So the project is open source, and our goal is to find vulnerabilities within it. And first, I would like to go quickly about what types of vulnerabilities we are after. So here are a couple of examples. Out of bound read write, double free, integer overflow, pass reversals, non-deferences, and more. Those are very interesting for us because those can lead potentially to remote code execution, and it is what we are after when we conduct the research on IoT devices and OT devices. So let's talk a little bit about the research methodology, and there is two main methodologies we can go with: is manual and automatic. So manual is when we are by hand going over all the code base and looking for the vulnerabilities that I have discussed before, and we did it for some extent, but it's not the best approach for such projects, and fairly quickly we went to the automatic approach, which is in most cases fuzzing. For all of you who are not familiar with fuzzing technique, fuzzing is merely a utility that feeds our program with random and unexpected input in goal to cause a crash. If our system is crashed, so we can know that there is a bug, and then a developer can look at this crash and deploy a fix for the bug. So it's like instead of going over the code base manually, we are going over all the code base automatically. And instead of a human being thinking about inputs that can feed the program, it is done automatically, and in this case, it is done better. So we will define fuzzing as a utility that has no prior knowledge about the fuzzed code, and our goal is, as I said, to discover vulnerabilities, and further does it in a lot of cases by extending the coverage, code-based coverage, with each input that he mutates, and we will see how it's done. So the fuzzer that we chose to go with is an AFL fuzzer, which is far more popular fuzzer today, and the workflow is very simple for that fuzzer. We start our fuzzer and we choose an input. We mutate the input until the program crashes. If crash of the program occurs, we will save the inputs that were responsible for the crash and continue with the loop. And a main brain of the fuzzer is to make each input meaningful. Instead of going of all permutations possible, which will take a very large amount of time, it won't be possible to do. Each input should lead us to a new code flow, and that's what AFL does very good, and that is why we chose them. So let's go over some AFL features. So first, one is very important. It's very powerful fuzzer. It discovered bugs in very high-profile executables like PHP, OpenSSL, and more. So it was very useful for very important programs. And as I said, the fuzzer is feedback based. So each iteration, each input that we put into a fuzzer needs to discover new code flows. And we can say that a fuzzer is done when no other code flows are discovered. And another one feature is that the fuzzer itself is source code-based fuzzer. It can fuzz binaries that are compiled, but it was designed to be source code fuzzer, and it works much better that way. So coming back to the Busybox, let's see the whole process that we will go through. First is what we need to do is to build a harness for any applet that we want to fuzz. A harness is only a small snippet of code that will connect the input to the fuzzer. So in our case, we will put our input in files, and we need to connect our Busybox to be able to get those input. So that is the harness. And the next stage is we need to compile our program with an AFL compiler. It is compiler that will put special instructions into our code without breaking the logic that will make that fuzzing possible. And the next step will be write a simple input for a fuzzer to start with. It needs to be some legitimate input that the program will expect, and the fuzzer will be mutate the input from their own. We will run the AFL in a controller agent manner. The more agents, the better. We will want to parallelize this further as long as we can, and we will stop the fuzzer when no code flows are discovered anymore. And after the fuzzer is stopped, we hopefully will see a lot of crashes. And those crashes need to be observed to take a unique subset of those. And that's what's called a triage. We will triage the results, and then we will get a unique list of the crashes, and we will go over each of them, and we discover what causes the crash and fix the bug. So let's see how a fuzzer looks in real in time of being at work. So we see that the numbers of things that we need to put our attention to is the number of code flows discovered. This is what I meant when I said that the fuzzer will be stopped when this number stays constant. And a number of crashes will appear here. And another thing that is pretty important is that we need to ensure that the speed of the fuzzer is sufficient. If it's too slow, it just takes too much time to complete, and we need to do something about it. Put it on a different machine, maybe put other harness or something like that. So that's how our computer looks like when the fuzzing procedure is taking place. And what we hopefully got, and we got 393 crashes, and now we need to triage them. We need to find a unique one. And how can we do it? To go over each of them by hand, it sounds like a very long task. So we will triage the results. We will look at them automatically and try to find what results are unique. And AFL provide such feature. It can does the minimization of the results, but we wanted to minimize the false positives, and we wrote a little Python script that will run every crash that was identified by NFL, and we will run it in GDB. We will take the stack trace and we will compare the stack traces with each other, and two stack traces that crashed at the same place on the same line of code and have something different in the middle, we will be considered as different crashes, and that is what we want to achieve. So from that number of crashes, we went to 21, which is pretty impressive. And now what we need to do is to look after each of them. And here's a table of all the bugs that we found. We can see the utility name along with type of the crash, along with the type of the crash that caused the instability, and we see is a CWE number as well, which indicates the type of the crash, and we can see that it is the same types that we see in the beginning. So we would now what we need to do is go one by one and understand the root cause of every crash, and we will do one of them right now, and we will do it on the manaplet, because the manaplet is very easy. The bug is straightforward, and we can follow it without going too deep into a code base. So a little bit about man. Man is an interface for a system reference manuals, and it has sections. In fact, it has 9 sections, and each section can be thought about a source of and use of the utilities that we are looking for. And here's an example of printf function. We have two printf functions, one of them in the first section and the other is in third. And those are totally different utilities. The left one is the one we can use in our terminal. Then the other is a libc function, which we use when we want to print something on the screen and to the file. And that is something that we need to consider when we look for a manual. So let's see how the command line looks like. So let's see the man of the man page, and we see that the man should be invoked by specifying the section and the page that we want to get a reference of. So, for example, man1 ls, we will invoke ls manual, which is a terminal section. And that's it for a man command line. So let's see how we can see how we can check and find the root cause of the crash. And back to the AFL results. AFL will, as I said, will save all the crashes that it found, and it looks like that in our directory. So what we need to do is just take this input and check if it's happening in original binary, is the one that was not compiled with AFL. If it does, it means that we have a stable crash. And that's what we check in here. We validate the crash, and we have a segmentation fault, what we hoped for. And right now we can go into the code and see what happened here. So it's pretty straightforward, and let's look on the function. So first we will, the man will query within the next argument is the section name. And the command that we will check on is man1. That's all, man1 without the executable of which we want to query the manual. And that's the bug. So when the function will query within the one is a section name, it gets true as an answer, and the pointer is advanced. And in here, we can see that the advanced pointer is being referenced. And in C program, when we reference a pointer that does not exist, the program crashes. And that's all. That's why the crash occurred, and AFL further found that bug. It wasn't found by hand. So we did this for every bug that we found, and we published. We did a disclosure to the maintainers of Busybox, and impact was pretty big, and it showed that the research was valuable for a community, which is what we hoped for. And soon after came the fix for the bug, and we see that the fix is very simple. It only checks that the pointer is really exist, and that's all. After this check, it won't proceed unless the next argument is exist within a command line. So that was the fix for the man applet. And that's it, actually. Let's summarize this research. So we found 14 vulnerabilities within Busybox applet, and some of them was potentially causing an RC. Not the man applet. The man was pretty safe, and it's only a bug, but we found some more interesting ones, and you are free to look at the blog post of Claroty to see which one. And Claroty responsibilities closed vulnerabilities with the maintainers, and it were fixed pretty quickly. And we have published a GitHub with all the harnesses that we have developed, and it is available within this link. So that's it. I'm free for questions if you have some.
Thank you so much, Vera. We really appreciate that. We're monitoring here for questions. I think we see one. Joe, you said you had one?
Sure, yeah. So I was curious, Vera, if you get more success from like purely automated fuzzing or from more directed analysis?
For a directed analysis with fuzzing, you mean, right?
Yeah.
Yeah, so it was directed because it's not because we fuzzed each specific applet differently, and we wrote a harness for each of them. It wasn't some harness that could be good for every applet. It was specifically for each of them. So I can say that it was pretty directly the way we did it, because every applet had a harness of its own, because it works differently.
So if anyone else has any questions, please drop it in Track 2 chat. We're more than happy to ask on your behalf. And we'll wait a little bit to give people a chance to fill out a question. When I first read your company name, Claroty, I read it as Carroty, just because that's what my brain does. And now I'm just thinking about a carrot mascot for Claroty, and it amuses me.
It's a Claroty for OT networks, because that's what a company does. So that's what.
And is that in collaboration with JFrog?
Yeah,
I saw.
Yeah. We collaborated with JFrog, and in fact, there is a blog similar to ours in their website. JFrog helped us to understand where a Busybox is deployed, and it helped us to understand the impact of our research. And it was very important because there is many targets that we can focus on, and it's very important to us to focus on those that will make a difference, that will be meaningful.
Yeah, I've actually been thinking about using, I think it's Artifactory is one of their products, but as a way to just kind of manage artifacts, and then, you know, if I find a vulnerability, check each artifact to see if that it exists in those artifacts. I haven't gotten too far with that, but I've definitely been looking at it. I think it'd be fun.
Yeah, so sure.
All right. Well, I didn't see anything pop up in chat. So Vera, thank you very much. That was wonderful.
Yeah, I enjoyed myself. Thank you.
Awesome.
Thank you, guys.